This is one of the structure I did a few years ago. So we're going to go ahead and design a base plate for the column, kind of similar to this one. And it's going to be for inside for building using W-shaped base plate. Be similar like this. We have a base plate over the footing. And because this is outside, normally we don't put grout underneath it, so the anchor bolt will not get deteriorated. And okay. So now we're going to go ahead and design a base plate just exactly the same as that's where you have the picture on screen. So here I have on my base plate, we have the concrete footing or concrete pedestal sitting on a footing. And then we have the base plate itself, and then we have the column. And the column is going to be W12 by 98. And the dead load we have is 115 kips for dead load, and live load is going to be 345 kips. And the problem is down bottom. Take a look at it. Okay, let's go to work and solve this problem. So now we're going to go ahead and go to the manual book and find all the information we want. The column was ASTM A992. That means we from the table 2, 4, and 2, 5 we see on the board. Yield stress is 50 KSI, and FU is 65 KSI. And the base plate that we're going to use is a A36 steel with FY is equal 36 and FU 58. Then we're going to look at the column itself. To go to table 1, get all the information that we need, which will be W12 by 98. Our D is going to be 12.7. B of flange is going to be 12.2, and thickness of the flange is 0.99 inch, and the web thickness is 0.55 inch. So now we're going to have the load, and we're going to take the load and we're going to bring it over here, show the load in load resistant factor design and allowable stress design. And we're going to use the code. Based on the code, the load resistant factor design is what you see on the board, and it's going to come out to so our PU is equal 1.2 times dead load of 115 kip plus 1.6 times live load 345 and equal 690 kip. And the allowable stresses, then we just add them. So it's going to be PA is equal 115 plus 345 equal 460 kip. The column base plate, we're going to use section AISC J8. Take a look at it on the board. And the phi factor and omega factor is different, and it's going to be phi is going to be 0.65, omega is going to be 2.31. So let's go ahead and do the equation J8-1. You can see on the board. I'm going to write down here. AT required. Is the required area for the base plate is going to be PU divided by phi C, and then 0.85 times F prime C, and F prime C, that's a 3,000 pound concrete, and the grout is going to be 4,000 pound concrete, 4,000 pounds, so it's not going to be a big deal, and therefore we're going to use 3,000 pound concrete here. And PU came out to 690, and omega C came out to be, for base column, is 0.65 per code, and we have 0.85, and then we have 3,000 PSI, and that is so the area came out to be 416 inch square, and I just came out 416. We're going to go ahead and do the same thing in allowable stress design. The area, we're going to go ahead and do allowable stress design, and the area is going to be, because we're going to divide by omega, so omega is going to be on top. Omega PA 0.85 F prime C, and omega is 2.31. Let me double check that. I was right. 2.31 times 460, divide that by 0.85 times 3,000, and area comes out to 417 inch square. 22. Per spec, we want to make sure this dimension that we have for the base plate is satisfy some of the requirement. For example, it has to be more than 3 inches, about 3 inches from the edge of the flange, and therefore we're going to say n is going to be 22 inch. Let me write this down now. And we want to satisfy this requirement. Right? We have said we're going to use 22 by 22 inches. We're going to make sure that 22 by 22 inches will satisfy our requirement, because we're going to have the anchor bolt someplace right here. And we want to make sure there is enough room, and therefore we want to satisfy this requirement. Our N, which is the base plate, better be bigger than D, and D is the 12.7 inches plus 2 times 3 inches here and 3 inches there. And also our B should be bigger than BF plus 2 times 3 inches. And if you plug in these numbers, it's going to come out to N is going to be bigger than D, came out to be 12.7 inches plus 2 times 3 is 6, and that is 18.7 inches, which is less than 22. That's good. And our B comes out to be BF, which is BF 12.2 plus 6, and that's 18.8, 18.2. Again, that's less than 22. Less than 22, so we okay on both of this. Base plate area, which is 22 by 22, that is equal 484, which is bigger than both 417 or 416. So we okay there too. I want to make, that was the area of the plate is 20 inch by 22. Let's make the area of the pedestal 24, add another 2 inches. So make it there, let's say area 2, it's going to be 24 by 24. Therefore, I'm going to make this here 24. It's not a good looking 2. Mm. 24 inches. Okay, let me erase this. We're going to continue. Going back to equation, this section J8, and our phi is a 0.65, omega is 2.31. We're going to calculate now the available bearing strength. And equation, I think it's the J8-2, gives us this basically as phi times P is equal phi C 0.85. If prime C AT, the area 2 divided by area 1, which is the base plate and the concrete underneath it, should be less than the phi times 1.c F prime C times AT. Let's do it. All right, so this becomes 0.65 times 0.85 times 3 KSI. The area is 22 by 22. That's a 484. 484 and time area 2, which is a 576 divided by 484. This 576 is a 24 by 24, the area of the pedestal, divided by the area of the base plate, and that comes out to, that should be less than or equal, well, let's see what it comes out anyway. So this is 875 kips, and that should be less than or equal 0.65 times 1.7 times 3 times 484. So which is 875 less than 1,600 kip. So we're going to use 875. So I just wrote this down so I don't have to go through this. I don't want to make the video too long. Here's the equation, same equation, but it's an allowable stress design. And plug in the number, it comes out to 583, less than 1,070 kips. Be a good exercise for you to try that, double check here. Come back, we're going to say, okay, we're going to use 875. If we use 875, it better be bigger than that number. Therefore, if I, in LFRD, if I use 875, bigger than 690, kept, so that's okay. And same thing here, if I use 583, but it'll be bigger than the applied load, so 583 is bigger than 460, so I am okay here too also. So I'm going to erase some of this here. I need more room. Next, there was the easy part done. So we're going to go ahead and calculate we found the dimension to be 22 by 22, but how thick that base plate has to be. So that's the next step we're going to calculate. We're going to go ahead and calculate the base plate thickness. Take a look at the section part, AISC part 14. It's pretty good reading anyway. And from there, we're going to use this equation to calculate that our M going to come out to N. N came out to be 22 inches, 22 minus 0.95, and D was 12.7, 12.7, and divide that by 2. So M is equal 4.97 inch. We're going to calculate N, which is equal. So next we're going to calculate N, B minus 0.8 times BF divided by 2. B was 22 again, minus 0.8 times BF came out to be 12.2, and divide that by 2. BN comes out to 6.12 inch. Next we're going to calculate N prime, which is square root of dBF divided by 4.7. 12.7 multiplied by 12.2 and divided by 4, and that comes out to 3.11 inch. Okay, so now we're going to go ahead and use equation 14, 6A and B in both load resistant factor design and allowable stress design. So we're going to move this thing over, and we're going to calculate X. I'm just going to write the formula down here. X is equal. So we're going to go, this is the equation for X. We're going to go ahead and calculate and equal. That's going to be 4 times D. D was 12.7 time BF was 12.2. 12.2, divide that by 12.7 plus 12.2 squared, and multiply it by PU, divided by, multiplied by PU came out 690. And our phi C times PP came out to, I erased it. If you go back a little bit, it was 875. So that multiplied by that is equal 0.788. And we're going to go ahead and take this formula B part and do it on allowable stress design. And X is going to come out to 4 times 12.7 times 12.2 divided by 12.7 plus 12.2 squared time omega is time 465.83, and this come out to 0.789, almost same thing. Equation 14.5, we're going to continue calculate lambda. Our lambda is equal 2 times square root of X divided by 1 plus square root of 1 minus X, and that should be equal or less than 1, which is equal. So we're going to go ahead and calculate lambda from this equation, and it's going to be 2 times square root of X. Let's use 0.788. And again, it's up to you whether you're comfortable this way or that way. But the number is so small, so that's going to make it different. But if I usually design, I kind of lean this way a little bit. So 2 times square root of x divided by 1 plus square root of 1 minus 0.788, and that comes out to 1.22, which is bigger than 1. So I can't spell 1. I'm going to use 1. A lot of time, the designer just go ahead and don't bother this equation, and they're going to use the conservative. They use lambda is equal 1. Continue with the equation. We're going to say lambda time n prime is equal 1 time n prime came out to be, forget what it was, 3.11. So this whole thing comes out to 3.11. So we did all the stuff so we can calculate L, which is the maximum of either m or n or lambda time n prime, as we saw at the beginning, explained in part 14. And I think the number came out, let me see if I remember what it was. It was max of m came out to be 497. N came out to be 612. And this one came out to be 311. So this one will control right here. So therefore, L is equal 6.12. Now let me erase this, and we do our final calculation for T. We're going to go ahead and calculate f of PU, which is equal to PU divided by B, and our PU came out to 690, and divide that by B came out to be 22 times 22, and that is equal 1.43 KSI. Here it's going to be f of PA, which is equal PA divided by Bn, so that comes out to 460 times 22 times 22 is equal 0.95 KSI. It comes down all to this equation here. We won't all do all this calculation because we didn't have L. And f of PU wasn't that difficult, but we needed to calculate that too. So our T minimum comes out to, our L came out to be, you said it was 6.12, and times square root of 2 times f of PU came out to be 1.43 KSI divided times 0.9 times FOI for the now remember, this FOI is for the base plate, which is 36 times 36, and that is equal, T is equal 1.82 inch. And we're going to come back and here do the same thing. T is equal, L came out to 612 times 1.67 times 2 times 0.95 and divided by 36. And T comes out to 1.82. Has to be like that. Bring this down a little bit. The 36 is underneath the bracket. So now we can use a plate 2 inch by 22 by 22. This was useful, and if it was, please give me a thumbs up. That way I know I did a good job.